upon first thought. Math being methodical and stark. Music being unrestrained and emotional. Even so, music can be explained using mathematical concepts. Starting from the basic fact that the sound wave of a pure tone can be represented using a sine curve, one can go on to examine the characteristics of music and even objectively define it. One of the most important features of music includes sound waves. Sound waves are patterns of disturbance caused by the movement of energy traveling through a medium as it propagates away from the source of the sound. The source can be any object that causes a vibration, such as a person's vocal cords or even a ringing telephone. This vibration disturbs the particles in the surrounding medium, and those particles disturb those next to them, and so on. The resulting pattern is a sound wave. Three important terms to know regarding sound waves include frequency, amplitude, and wavelength. The frequency of a sound wave expresses the number of cycles the wave goes through per unit of time. The amplitude represents the distance from the rest position to the crest position on a specific wave. The wavelength is the distance between two successive compressions. A high amplitude results in a louder sound, while a low amplitude results in a softer sound. A short wavelength results in higher frequencies and higher pitches, while a long wavelength results in lower frequencies and lower pitches. Two relevant theories, the particle theory of matter and the kinetic molecular theory, will help analyze if sound waves ever settle down and whether or not reaching dead silence or complete silence is possible. The particle theory of matter essentially explains that all matter is made of tiny particles and that these tiny particles are always moving, similar to perceptual motion. Each pure substance has its own kind of particle, and the particle theory of matter helps explain why solid particles are packed tightly together and why gas particles are packed loosely together. The kinetic molecular theory says that particles are in constant but random motion and are always colliding with each other or walls. Despite these collisions, there are no interactions between the particles, including attractions and repulsions. So, do sound waves ever settle down? Is approaching dead silence possible? Or in terms of calculus, does the limit of the sound wave ever approach zero as time reaches infinity? By the perpetual motion theory, particles will never stop moving. However, even if there's no apparent sound, are there still sound particles in the air? As long as Earth is still spinning, there will always be vibrations from outside forces, whether noticeable or not. Dead silence to a person might not be dead silence to other animals, such as dogs, since the pitches we can hear are different than those of dogs. As a result, dead silence is not achievable, and the limit of the sound wave will never approach zero as time reaches infinity.
That's music on the particle level, but what about sound waves as a whole? Using math, we can define music as tones possessing a constant oscillation at a given frequency. It's clear to see how pure tones have a constant oscillation, given they can be represented by a sine graph, but what happens when sound waves are combined? In this case, the principle of linear superposition can help us understand how sound waves interact. It states that the total displacement that occurs when two or more waves simultaneously occupy the same space is equal to the sum of the displacements of each individual wave. Basically, they just add up. Although the result is no longer a perfect sine graph, it is still a periodic function, and each frequency is distinguishable when heard. This explains why we can discriminate between chords and general noise, for the sounds resulting from noise possess waves at so many frequencies that the resulting combination has a practically non-existent period. Speaking of chords, we can also use math to predict which ones will sound the most consonant. It's all in the frequency ratio hypothesis. Although ratios can be formed from all note intervals, this hypothesis states that the most consonant chords are made up of notes whose frequencies can be reduced to the simplest ratios. That's why a major third is more pleasant than a minor second. However, there is one peculiar exception to this hypothesis. When played together, A flat and C, a major third, sound much less consonant than A sharp and B, a minor second. There are tons of other theories about consonance and dissonance that make up for this hole in the frequency ratio hypothesis, but they deal with cognition, cultural norms, and the biological aspects of the auditory system, so we're not going to deal with them. After all, math can't solve everything.